and it shall remove, and nothing shall be impossible unto you. And I want to reiterate that part. Nothing, right? Nothing shall be impossible unto you. Now, students, you're going to do your exams. I want you to know that, as long as you study and you put your trust in God, right? Put your trust in God. There's nothing will, hinder you from, remembering the information to put on that paper, right? So just be of good courage, right? Your faith in God will affect anything. Your faith, you must have faith. You must have the belief that God is able, right? Make sure you study, right? Don't set up yourself. Make sure you study. Have faith in God, and everything will be okay, right? So let us pray. Father in heaven, we want to give you thanks and praise for being such a good and awesome God. Lord, we give you thanks for all the students who are gathered here this morning and the teachers. We ask you, Lord, that your Holy Spirit will direct their thoughts, and that, Lord, everything that they will go through, they will have full understanding. We ask you now to have your own sweet way. In Jesus' name, amen.
Amen.
All right, Brother Dawkins, over to you.
Thank you so much, Sister Hamilton. All right, so again, just like to extend a welcome to each and everyone here on this platform, and a good morning where you are. Where I am at right now, it's not morning, but nonetheless, it's a bright and sunny day. All right, so I see here 22 participants, inclusive of myself. I take it that, well, there's a host, and then there's me, and then there's Sister Hamilton. So I take it that 23. So there are about 20 of you here who have elected to join this platform for this session. Now, this session is going to be 2 hours long, and as such, we want to see if we can maximize on the interaction as best as we can. Normally, when I keep these kinds of sessions, I focus on past paper style questions, because if we were to take the 2 hours and try to go through or try to address any issues that persons are having, then it would work out to be probably as many as 20 hours and not 2. So I will now elect to go through past paper. Ideally, I'd want to go through a paper 2 and a paper 1, but seeing that paper 2 comes before paper 1, we're going to see how quickly we can now run through the paper 2s. And if time allows, then we'll see if we can get through a paper 1. Right, seeing it is that it is only 1 session. All right, now, as it relates to the paper, I don't know how many persons here would have access to it, but I do have access to the last year's paper. Is there anyone here by way of show of hand or by texting in the chat that does not have the last year 2021 paper 2 for CSEC physics? Indicate so. All right. What I will do, I will try to see. All right, I see the hands going up. 2 hands there. 3. All right, 4. All right. So what I'll do, 5. What I'll do is I will make this paper available. Let's see now, how does Zoom work with this? Can I share files here that persons could access from here and download? Somebody let me know. I'm not so familiar if that is possible. I could just directly share it here. All right, hands down for those who put up your hands. Anybody? Mr. Hamilton, you could help me out here. You can share the link. As in what, from Google Docs? All right, let me see if I can access it in my Google Docs. Let's see, Drive. Let me just get that out the way before I proceed with anything. Ensure that you have this paper in and of itself. All right, let's see, the CSEC paper 2 here. Let's see, get link, copy link. Hopefully this works. Chat from where you downloaded it. You can share the link. All right, what I'm gonna do is, this is the Google Doc link to it. All right, hopefully that can be accessed and persons. Somebody could just try to see if that link is accessible. In the meanwhile, what I will do is to share screen with the actual paper. All right, are we all seeing the paper here now? Confirm somebody? Should be. Okay, that's a yes. All right, so this is the last year's paper. All right, what I'm gonna ask is for persons who have their hands up still, if you could lower it, so if there's a point that I could just know, right? So like Kimali, if you still have your hand up, if it's a point that you want to make, then I can acknowledge. Failing that, could you just lower your hand so I could know when there are issues that may arise. All right, thanks. Good. All right, so as I was saying, with regards to this paper, this is the last year's paper, 2021. And if you're not yet familiar with the structure of the past paper questions, it is 6 questions in 2 sections. You have to answer all. You have to write in the spaces provided, so on and so forth. Question 1 is always a 25-mark graph style question, always. If you have any access to any past papers and you check the number 1 for all of the, and this is a standard thing for CSEC, chemistry, biology, physics, sciences. Question 1, 25 marks, graph-based question. All right, so with this question, CSEC had elected last year to choose Hooke's law, right, to center their graph-based question around, right? And this is an interactive session. I know that some of you now prefer not to open mics and all of that, the whole shyness, I get that. But I'd really want persons now to speak back to me as it relates to, answering this question. It's not just about me talking, and you saying, all right, yes, because I'm a teacher. I'd like to hear from you, as quickly as possible. So when I ask a question, somebody just throw out a response, whether in the chat or opening their mics, or tell them what they're thinking. And there's no wrong or right here. No judgment is held. If you say something and it's incorrect, we're here to know, just fix it up. If it is correct, that's good. If it's not, then we can fix it. All right, so in terms of Hooke's law, the statement for it, 3 marks. I have to pay attention to the mark scheme, the mark allocation rather, because it indicates now how it's going to be marked for, right? Because typically, especially with sciences, more so physics, you're looking for key terms, key phrases to award marks. So always pay attention to what they ask for and the number of marks that are given, and then it can now give you an idea as to what or how you approach the question. All right, so Hooke's law, 3 marks, 3 key things that must be mentioned. Somebody talk to me as to what? All right, the extension of a spring is directly proportional to the applied force provided the elastic limit is not exceeded. Hakeem. Hooke's law states that the force applied to a string or an elastic is proportional to extension. Latavia. All right. Hooke's law states that the force is directly proportional to the extension. All right. So Amara, Latavia, yes, you're on point, but there's something lacking, and Hakeem addressed that, provided that the elastic limit is not exceeded. That is a key thing that you have to mention as it relates to giving responses to Hooke's law. all right, you have to mention that the elastic limit is not exceeded because 1 point, the force applied, 2 points, directly proportional to extension, and the third is also that the elastic limit is not exceeded. All right, so we're good there for our 3 marks. All right, for this question now, my challenge here is how to go through a graph style question on this platform. Normally what I do is that I rely on actual, what is this? An actual online graph paper, right? Just to see how best we can kind of sketch it to show what, you know, the whole graph would look like. I'm yet to find an effective one as to how we can use graph virtual. Let's see now. No, not that one. I'm just trying to find the one that I normally use, sketching a grid. All right, let's see now. See if I can probably move this here. It's really a challenge sometimes to do this, but this thing needs to stop. All right, let me just get rid of this, minimize that. All right, so before we even get to that, we're talking about interpretation here. Now, with regards to the table, there are 4 slots that are to be filled for the force and 3 for the extension. And you'd read the instructions above, fine, and it will tell you pretty much what is expected. Now, as it relates to the column for force, you're given mass. Now, how would anyone here make the approach as to trying to find the force, given the data that they have there? All right, force is equal to mass divided by gravity. Almost close, Newton, Akeem. Force, yes, and mass and gravity all go together, but it's times. So force, right, that's it, good. So force times gravity, mass times gravity gives us force. So we essentially know the gravity constant is taken as 10 Newton per kilogram. Just to verify, you know, state it there. Usually the constant is given somewhere along the line, but it didn't state it, but you can take it as 10 Newton per kilogram for gravity. So essentially all the mass values there are multiplied by 10 to give you your force. So that's 1.0, 2.0, 3.0, 4.2, 5.0 for your force. Now for your extension, what would you do to get those values? Not a problem, Aki, not a problem. Anybody else? As it relates to how we find extension there? Any suggestions?
Sir, how you got the 4.2, you subtract the 70.0 centimeter from 74.4 to get the 4.2 as an extension.
Right, good. So what would you do now going down now? All right, so subtract the other lengths from the original. All right, yes, Amaria, correct. So we see here, and that's very important, some persons made the mistake of subtracting successive points, meaning that 70.2 from 74.4 gives that, and then they go again now and say 74.4 from 79.2, and then each pair successively they subtract. No, the spring has an original length of, is it a spring? Yes. The spring has an original length of 70.2. How do we know it's the original length? When there's no load, no force, no mass attached to it, it's unstretched. So that's its original length. And that original length is the length that you always use to subtract to get the new from the new length to find the extension. Make sense? If something is originally of a length and you add something to it, it gets longer. To find the extension, you always take the reference original length from the new length to find the extension. So the values going down would be, I should have these reference. Where am I? Where am I?
9, sir. 9, then 13.7, then 18,
okay,
and 22.5.
All right, so you have done the math there. Excellent. Now, as it relates to plotting the points for the graph, so doing that scores you 4 marks. Easy 4 marks, right? Now, in terms of the graph itself, a common misconception is that persons now jump and just plot the points or label the axis in any random way. No, The instructions always, and it's a good thing that it hints at it, the instructions always tell you which quantity goes on which axis. What do I mean? A graph is always this versus that. Y versus X, that's a standard. Once you plotted a graph, it's always Y versus X. And instructions will always tell you what is Y and what is X. So in this case, it says plot a graph of extension E versus force F. Typically for Hooke's law graphs, it is force versus extension. But in this case, it is extension versus force. So what goes on the y-axis is not force, but extension. And what goes on the x-axis is force. So you have to pay attention to the instructions given in the question to plot the graph to know what goes where. Now, the next thing that we need to determine, so we know what is going where. The next thing we need to do now, because we're striking for maximum marks, is to develop an appropriate scale. Now, typically the graph page, you can count out the number of squares that are available. A standard graph page has about 23 centimeters vertically and about 18 centimeters horizontally. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then you should have about 21, 22. So you have on your vertical 22, 23 centimeters to play with, and you have 16 on the horizontal. So your trick now is to find a scale that is able to spread out your data range as much as possible without it falling off, and to not ensure to avoid your values being too bundled together. All right, so you have to find that balance point where you can now spread the points out and everything fits, but at the same time, you don't want to make it too small, because CXC marks for at least 75% of the graph being used up, the graph page. So that's actually something that they look out for and they're marking for it. All right, so you don't want to pick a scale that is suitable for you, but doesn't use up the graph page as much as possible. Now, we're putting extension, the range of 0 to, what was the last one? That was about 22.5. 22.5. So we are fitting 0 to 22.5 on the vertical, right? And we're fitting now the force range of up to 5 on the horizontal. Now, some persons may jump and say, all right, 1 to 1, meaning 1 centimeter to 1. So that's 1, 2, 3, 4, 5. And then for the extension, they'll probably do the same thing or probably make it a bit short. And they say, all right, cool. And they just plot the points and they don't know. You have to spread out your values. Now, as it relates to the extension, it's a good range of values, 22.5. So I believe, let me see, 1, 2, 3, 4, 5, 6, 7, 8. Then that's 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. About 22 there. So a 1-to-1 may not necessarily work, meaning that counting up 1, 2, 3, 4 going up to 22, because we have to fit 22.5. So what I'd recommend is that you could use now a 2-to-1. It's a trial and error, but with practice, you easily can get to it. So what I'd recommend here is a 2-to-1, meaning that a value of 2 centimeters of extension to 1 centimeter of graph. So that means that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. What you could do is that later on, you could just try the graph for yourself, plot it, see what you get, and all of that. All right. As I said, it's really a matter of, where I am right now, I don't have a graph paper, and I should have just have this plotted and all of that for you to see what's the result of it. But I take it that persons are at this point now capable of plotting these simple graphs, so you can just practice it for yourself. It's just a concept now I'm explaining to you. All right, so as it relates to this on the y-axis, you're going to write, you're going to use a 2-to-1, meaning 2 centimeters of extension to 1 centimeter of graph, and then you label your points all the way up to 24, right? 26 if you want to stop. And then for the x-axis now, as I said, you have as many as 16, so you wouldn't use 1-to-1, as in 1 Newton to 1 centimeter. What you could use is a 2-to-1, meaning that 2 centimeters to 1 Newton. So that'd be 1, 2, 3, 4, 5. The 3 to 1 could even work. Because you could have 1, 2, 3, 1, 2, 3, 1, 2, 3. So you could go as many as out of 5. But here's a challenge now with using numbers like 3. Is if you're finding in between points like this 4.2, and you're working with 3 centimeters, it's kind of hard to find the in-between points. So stick with whole numbers, 2 to 1, 4 to 1, 1 to 1, 5 to 1, because in between there are some small lines that lie in between here, right? So you use those kinds of numbers that make finding in-between points easy. Not to say that you must, it's just that finding the in-between points, it makes your life a little bit easier. So we could use a 2 centimeter to 1 Newton, or even 3 centimeters to 1 Newton here. Because as I said, it stops at 16. So like 15 centimeters would fit 5. So you could use that if you want to spread it out. If you want to use a 2 to 1, I believe you could get away with it because it still uses up a good portion of the graph paper. All right, so you could use that and get your points in. You plot your points. Now, the concept of a best fit line is what I want to bring to your attention, because as it relates to plotting best fit lines, I want to ensure that persons understand the concept of a best fit line. Now, if you have points, and this is going to be a best fit line, it's not going to be a line, a graph that is going to have the points falling nicely on it. Sadly, but it's not going to be like that. So what do you do now when you find the best, the points skewed or deviated from ideal, and you know you want to draw that best fit line? And of course, how to find the gradient. Not assuming anything here. We're covering as many bases as possible, because probably some persons now are not so clear on that. So we want to ensure that we cover bases there. All right, so as it relates to the best fit line concept, say you have points that are like this, and then ones like that, and then they're not falling on the line as you'd want them to. All right, but that's all right, because experimental error will dictate that your points may not necessarily always fall on it. And then typically, I believe it's a minimum of 5 points that are required for you to plot a real graph. We have 6 here, and I think the table, right, gives us how many points? 1, 2, 3, 4, 5, 6, 7. No, 6, right? So we're good there. Now, the first point, which I should have included, is how for this kind of graph is a 0, 0 point. Ensure you plot your 0, 0 if it is given. All right, make sure you plot your 0, 0 if it is given, and it is given there. Now, as it relates to your best fit line, when you join a best fit line, ensure you take a ruler. Must take a ruler, and then you draw a line that best fits your points. Now, I'm going to draw this line as you would with a ruler. I'm going to color it red. And the concept of the best fit line is that you don't necessarily have to get as many points on it. What you want is a line that when you check it, all the points simultaneously come as close as possible to that line. Because the best fit line is that line that you would get if the points were perfect. But because of experimental error, you're gonna get deviations. Do we connect the dots? No. Do we try and skew it to one side and leave out other points? You know, like discriminate to get the points. All right, then the point say, you have one out there, so it don't look like you can line up, so we're gonna leave the one out there, so we're gonna line up the other 5. No. What you need to do is to draw a line that comes as close as possible to all the lines at the same time. So when you look at, all right, the first one, good. The second one, all right. The third one, yeah, it's out. But when you look at the fourth one, it's also out on the other side by the same degree. So when you check it out now, nobody's really left out there. You don't skew it to one side or the other to accommodate the third or the fourth. You put it in the middle. And the same thing for the 5th and the 6th. So this now, and of course, everybody will get different types of best fit lines, but the concept of a best fit line is to ensure that you draw a straight line, ruler, straight line, And that line now comes as close as possible to all the points that are there. Now, once you've drawn a best fit line of your points, then what you do is to find your gradient points. Now, your gradient points, I usually say to students, you want to draw from a coordinate down. Let me change the color on this. You want to draw from the coordinate down and from the same coordinate straight across. I know that persons are taught differently. You use a triangle, you use points that are plotted, but typically I always say use random points, and these random points now should be spread out as much as possible. Meaning the coordinate that you choose, the next coordinate should be far away from it. Now, the reason why, rationale behind my saying this is, remember the best fit line is the ideal line. So what you're trying to do now is to find that gradient that is an average now of your experimental data. All right, so once we'd have done that, we would have now found in theory that those set of coordinates that would now best approximate what you should have gotten had you done the experiment perfectly. And we're human, so don't worry about making mistakes. It's a part of it. Now, in terms of the gradient points, you should always label them correctly. And once you have labeled them correctly, then you highlight what is what. All right. Now, I don't encourage persons to use points that are part of the data table because, as I said, these are subject to error. But the best fit line now kind of minimizes that error. So always use coordinates from your best fit line. Well, I encourage you. And then some persons may stick out and say directly that they want you to do that. So to be on the safe side, just use the coordinates from the best fit line and not from your data table. All right, in terms of the gradient now, right? Some persons call it G, some call it M, but it's really mathematically the symbol is M. Y is equal to mx plus c, yeah? Can anyone now recall, sir, if it says to plot speed against time, which one would be on the y-axis? Speed would be on the not speed. Speed against time, yes, it would be on the y-axis. Speed would be on the y-axis there. All right. Vidor, I believe that, yes. So it's always one versus that. Against versus is always y versus x, y against x. So if they say speed against time, Vidor, then it is speed on the y-axis. All right, the equation there, y2 minus 1, correct? Good, thank you, dear Akeem. So y2 minus y1 over x2 minus x1 is our gradient value. All right. I know some persons may say, you may be probably taught y1 minus y2 over x1 minus x2, but here's a challenge now with that. Your graph always progresses from the origin outwards, or rather, let me say it this way, from your initial values to your final values. Your initial values are here, your final values here. So the graph trends from bottom left to top right. And for you to find the gradient, it is rise over run. And rise is always the change of y over the change of x. And change is always final minus initial. So when it boils down to it, you must find your initial values and final values of y and x. And the final values are the values that are out from the origin, are from where the initial points are, and the initial points are closer to it. So the logic of it is y2 minus y1 over x2 minus x1. Now, when you would have done this correctly, picking the coordinate points, you should end up with, because I was working through this, you should end up with a value of about 4.09 for your answer, thereabout, plus or minus, because they give a range, because everybody's going to draw their best fit line differently, so they will give a range, but it's somewhere along this line, plus or minus like probably 0.1, 0.2, depending. Now, in terms of the axis, the units of the gradient, because there are 4 marks for the gradient. First thing for the graph plotting, in terms of the gradient workout rather, to recall the equation correctly is 1 mark. So this y2 minus y1 over x2, that's 1 mark automatically. To substitute your y2 and y1 values, identify and substitute them, that's another mark. To correctly calculate the gradient within range is another mark, 3 marks, and then the units of the gradient is your final mark. Now, we're going to label this. This is extension. I'm going to use just the symbols for the sake of avoiding to write this. And the unit of extension here was given as centimeters. And the x-axis, yeah, was force, which was Newton. Now, let me ask, what would be the units of the gradient? 4.3. All right. If you got 4. As I said, it's a plus or minus value, because when I did the math, I didn't actually plot it. I just used the data from the table. But yes, thank you there, Carissa. Now, can anyone tell me what the units of the gradient would be here? Centimeter per Newton. That is correct. Newton per centimeter. No, Jonathan. Here's the thing. We're plotting y versus x. So the units of the y would be divided by the units of the x. So it is the centimeter in the y in the numerator over the Newton on the x. So it's actually centimeter per Newton and not Newton per centimeter. All right. So to be sure as to what the units of the gradient are, look at what the units of the axes are. And always put the y units over the x unit. No matter how it might look incorrect, always do that. All right. Y units over x units are your gradient units. All right. So whereas Carissa, yes, centimeter per Newton, that is correct. All right. So we are at now the other part of the question. Where is it? Here we are. All right. So we have done part 2 here, 8 marks. We have done part C here, 4 marks. Now it says, given that the gradient is 1s is 1 over k, find the spring constant. What would you do there?
So you'd have to transpose the formula.
Right. All right. Here's the thing now with the title. Yes, because based on the 8 mark range, yes, I got to put in the title. Thank you there, Vidor. The title should have been put in. The title there would have been graph showing where is it? All right.
Extension versus.
Right. Graph showing extension versus force, or graph showing extension versus load, if you so. Right. But yes, in term, because how I would mark this is the plotting would have 1 mark, the best fit line 1 mark, 2 marks. The scale, I would give about the label of the axis 2 marks, the scale 2 marks, so that's 6 marks. The title would be another mark, and probably finding the gradient points another mark. But when you see an 8 mark graph, always put the title on the graph. All right. But yes, thank you for that there. Indeed, you should have put the title on the graph there. I saw somebody in the chat saying something. I don't know where it went. Oh yeah, sorry. I'm gonna bring it back up. Where is it now? Right. So I'm saying now for the title, put it in. Put everything in. Good. Now, somebody had responded about the 1 over k. So we invert the value of 4.3 or 4.09, wherever, and then whatever that gives us would be the k value. And the k value now would, of course, be, if we use that 1 over 3, that I believe, was it that I'd given me that 1 over 4.3? Carissa, right? We use that value for Carissa for 4.3. We would get 0.23. And the units, of course, would just be the units of the gradient inverted. So if the units of the gradient were inverted, what would the units of the k value be? Anybody? Nobody? Okay, Newton per centimeter. Thank you, Deru. What was another response? Was
Excuse
there
me,
one
where
over
on the
3?
calculator would you press to invert it?
Say again?
What on the calculator would you press to invert the value of 4.3?
No, man, what you could do is just to put 1 over 4.3.
Oh,
I
okay.
don't know of a button on the calculator that is able to invert a number. Probably there is, I'm not so sure. But when you talk about invert, we simply just put 1 over that value. So it's 1 over 4.3 as Trey had suggested there. And that would give 0.23. And of course, Rue there has pointed out the units of Newton per centimeter being the correct units. All right, now, here's where we have to now apply our little ingenuity a bit. It says, given that F is equal to KE, where F is force, K is the spring constant, just calculated 0.23 Newton per centimeter, and E is the extension, it says calculate the length. Let me just point out here, it does not say calculate the extension. It says calculate the length, L, when a force of 8 newtons is applied, assume that the spring obeys Hooke's law for 3 marks. Now, how would this be solved? Anybody?
Sir, first you'd have to transpose the formula, which is F equal KE to get
Good.
E
Right.
as the subject.
All right. So what we could do then is to work that out. All right. So what I'm going to do now is to go to the screen share of my, please be up, where is it? All right, let me try this again. I want to close this out. Here we are. All right, so what you could do here is to say transpose for extension. An extension, the equation for extension would be Akeem. Was you that responded, Akeem? I'm not sure what spoke.
Yes, sir. Could you repeat the question?
Now I'm saying when you transpose the F is equal to KEX equation for extension, what do you get?
E equal F over K.
Good. So what is the F value that we're using? What F value we're
8
using?
Newton.
8
8
newtons.
newtons.
Good. And what is the K value that we worked out?
4.3.
0.2 from the previous question.
No. What did he say the K1 was, Carissa?
0.23.
0.23. So we divide 8 newtons by 0.23. That 23. And we get 34.78, roughly 34.8 centimeters of extension. Is that our answer?
Yes, sir.
Yes, sir.
No.
All right. Here, I think that was Carissa. I did say no, Carissa. Marissa as well. What have we found when we divided force by K?
E extension,
What did the question ask us for?
length,
Length. So what do we do now to find this length, knowing extension?
You add the original length to the extension.
Thank you, dear Carissa. Remember, the spring always has an original length, and then from the original length, there is a new length when we add forces, and then from the original length and new length, we get extension. So what they're asking you for here is that length when 8 newtons has been attached. But the original length will always be there. And the extension is what we just calculated. So we must add the 34.8 centimeters of extension to the original length to find the actual length of the spring. All right. So I am saying 8 newtons is applied to the spring. The extension is 34.78, 34.8. They asked us for the length of the spring when the 8 Newton force is applied. They did not ask us for the extension. They asked us for the length. So that's what I'm saying now, you have to pay attention to what you're asked for. Because as I just realized, And I figured that persons would have fallen in the trap. Some persons work with the extension and say, I hit that. No, that is not where it is. You have to now take that 34.8 and add it to the 70.2 centimeters of original length, and that gives you now a total length of 105 centimeters. That is the length of the spring when the 8 newtons is applied. Are we all clear?
We get
Yes, sir.
34.8, sir.
4.8?
We get 34.8.
All right, when we worked out, let's go again. We had 8 newtons divided by the spring constant of 0.23. Because when we transpose for extension, E is equal to F over K. The F value is 8 newtons. The K value is 0.3 that we found in the previous question. So when we divided force by K, we get 34.78, rounded off 34.8. That is the extension produced by the 8 Newton force. You with me so far, Vidor?
Yes, sir. Yes, sir.
Good. When I ask the question, have we found our answer for the length of the spring? Some said yes, some said no. And the reason why it is actually no is because all we have found is the extension. We have not found the length. Because the spring has a length when there is no force. So to find the length when there is a force, we must add the length, the original length, to the extension produced. So the overall length would be the 34.8 of extension plus the 70.2, which gives a total length of 105 centimeters. That is the length of the spring when the force of 8 newtons is applied. Understood?
Yes, sir.
Good. All right. So let us proceed now to question number 2. Question number 2 was also a little curveball in that they sent 2 topics that are not typically topics for question set. So I realize that they kind of threw persons off here. But nonetheless, it's a part of physics, so we have to prepare ourselves. But we can probably take comfort in the fact that if it came last year, then more than likely it won't show up this year. But don't take my word for it. I'm just assuming here. So we have to prepare. So it says here, define each of the following terms. We have moment of a force and we have center of gravity. Now, as it relates to defining moment of a force, what would be your answer for that definition? Anyone? Nobody remembered about moment of a force?
Say it's in the chat.
Oh,
Say it's in the chat.
I will just assume it. Okay. Oh, a moment of a force is the measure of the turning effect on a force or the product of the force on the perpendicular distance. For torque, moment. All right, good. Yeah, yeah. I'm just responding to person's request for share of the past paper there. Let's give me a minute here. All right, so yes, these are all correct. Center of gravity now. What would you define center of gravity as being?
Sir, it's the point through which the weight of an object is considered to act.
All right, point where the mass of the body is concentrated. Center of gravity is the point in the body where the mass is more concentrated. Or yes, indeed, it is a point where the weight or mass seems to be acting. Yeah, these are all correct in your definitions. All right, so 2 marks there for center of gravity, moment of a force, turning effect of a force on a pivoted object. Good. State 2 conditions necessary for a body to be in equilibrium. Oh, this is interesting. Let me ask now, what would you say for here?
One would be that the sum of the clockwise moments is equal to the sum of the counterclockwise moments.
Good. No, Akeem, not last service here. Yes, Carissa, that is one condition. What's the other? The resultant force acting on the body is zero. Thank you, dear Marissa. So yes, the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments on a pivoted object. And two, as Marissa pointed out, the resultant force or the sum of forces acting on a body must be zero. So those are the two conditions needed for equilibrium. Forces that prevent motion and turning effects that must be equal to prevent rotation. All right, now, I don't know if persons are familiar with these types of diagram, but we're going to flesh it out and see what happens. Figure 2 shows a diagram of a non-uniform plank. Non-uniform plank meaning that its center of gravity is not at the center of the object. So it's heavy on one side. So when you talk about objects that are uniform or non-uniform, a uniform object, the center of mass is directly at the center of the object, geometric center. Non-uniform means that it is to one side, it's not dead center. So we have a non-uniform plank AB, which is 2 meters long, right? So the entire length of it is 2 meters. You see, in these moments of principal and moments question, pay attention to all data. Everything that's given, pay attention to it. So it's 2 meters long, A to B. It is non-uniform, so the center of gravity is offset, as you can see here at C. It's not in the center, it's offset. And it weighs 1,000 newtons, which is identified there as W. The plank is supported from a ceiling by 2 vertical springs, P and Q. The plank is attached at a distance of 0.5 meters from each end. C is the center of gravity, as I said. Now, when a plank is horizontal, the tension in spring P is 600 newtons. Calculate the tension in spring Q. I have to show all working. Now, before you even start bursting your brains to figure out what is going on, pay attention to the mark scheme. 2 marks. That's not a lot of workout. So my approach here would not initially be try to figure out the moment that is acting here. What I would do now is to consider how else I could find the tension or force in spring Q apart from using a moments approach. Now, let me ask. All right, Akeem, you're getting it. Total upward force equal total downward force. That is the thing. Remember, we had asked the conditions for equilibrium. And we said that moments, sum of moments must be 0, and the sum of forces must be 0. So if we don't want to take a moment approach to find an unknown force, we can take a sum of forces approach. And as Akeem had correctly said, the sum of upward force is equal to the sum of downward forces. So with that being said then, Akeem, what would be the force in Q? Or in any person therefore. I didn't get that. I didn't get that part. Nobody's responding. Neither chat, no. Okay. 1,000 minus 600, 400. So 3. All right. Correct. So the 1,000 newtons is down. That's the total downward force. The total upward force is from P and Q. If P is providing 600, then Q must provide the balance. So we just simply take 600 from 1,000, and the answer there would be 400 newtons provided by Q. If you required more marks, then probably you could take a moments approach if there were more unknowns, but try to find the simplest route to your answer. All right, try to find the simplest way to give your answer. Now, here's where it's not as simple. By taking moments about A, determine the horizontal distance from P to C.
Excuse me, sir.
Yes, Jonathan.
You can repeat what you did for the first one, sir.
All right, what we did was that we applied the concept of sum of forces must be 0. And the sum of forces are the upward forces added to the downward forces. And because they're opposite, one is the negative of the other. So if you want to consider up as being positive, then P provides a positive 600 newtons. Q is the unknown, and the downward force is negative 1,000. So to find what the overall force is, we simply know, just say, all right, downward force is equal upward forces. P plus Q is equal to W. 600 plus Q is equal to 1,000. So Q is equal to 1,000 minus 600. So Q is equal to 400. Understood?
Right, sir. Yes, sir.
Good. Now, as it relates to taking moments about A, your point here is A. Or taking moments about that point. So we want to find out what the distance of P to C is. Now, can anyone, I got 400, yes, correct. So clockwise movement equal anti-clockwise movement for the next one. That is correct. But how do we work this out? All right. Here's the thing, because I know that the responses are going to be a bit varied, we might be here on the question for a bit more than I'd want it. What I will do is that I would outline as to how we now approach this question. All right, so we're going back to the whiteboard to see how we can now figure this bit out. All right, let's see now, let's zoom this back out. Let me erase all of this. I'm going to reproduce the diagram here as quickly as I can. Make that a bit thick. All right, so we have in this corner, I believe this was, no. All right, we had A. Then I believe P was here. And we had C, which had double below it. Then we had B at this end. Then we had Q somewhere here. Good. And I believe those were the points. A, B, C, P, and Q. Right. Now, in terms of A, they say we're going to take here as the pivot. So let's just identify here as our pivot. Typically, we use a triangle to identify the pivot. We're going to identify our forces now from C, point C. We have double acting there. We have point P providing an upward force. And then we have Q also providing an upward force. Hold on, wait, you're not seeing? Hold on, let me see something. Hold on, wait. It's interesting. Hold on, wait. What is anyone else seeing? I'm not sure what the challenge is. Okay, you can see it now. Okay, all right, everybody's seeing. All right, lovely. All right, so let's get back to it. Right. So these are your forces, and then we can now put in our varied distances. From, see now, let's see who's this. So we have this gap, right, which we know is 0.5. All right. What else do we know? We know that the gap here to here is also 0.5. We know the entire gap from here all the way over to here is 2 meters.
Answer, the distance between the weight, the downward weight, and Q could be 1, since as the other distances are 0.5.
Downward weight to Q?
Yes, sir, it could be 1 meter.
Yeah, because in the question it said that see what other data was given. No, hold on, wait. What other data? 2 meters long, 0.5, 0.5.
Well,
C is
no, not from the weight, from P to Q rather. Would be 1.
Oh, you mean from P to Q?
Yes, sir. Yes, sir.
Yeah, right. And then from P to Q would be 1 meter. Because if each of them is 0.5 and the entire thing is 2, then this here is 1 meter. All right, good. So we know these distances based on the data given and what we have interpreted there. And our job now is to find what this distance is. P to C. All right, so that we say is the unknown. All right, so here's the thing. For us to do principle of moments, we have to identify our forces and our distances of the forces from pivot. All right, we have to identify the forces and the distance of the forces from our pivot point. Let's zoom this out, stretch this across here. Good. All right, so our forces are P, Q, and C. Our pivot point is A. My question to you is, which of the forces would provide one to rotate this plank clockwise and which one anti-clockwise? P and Q go the same way. Are P and Q clockwise or anti-clockwise?
They're anti-clockwise.
Right, so P and Q are anti-clockwise and they go the same way. So therefore C there is clockwise. So what we say in our response is that clockwise moment and the sum, use the summation sign in this case. All right, the sum of the clockwise moments
Equal to sum of the anti-clockwise moment.
that is correct. But we only have one clockwise moment, so it kind of makes it simple there. All right, now in terms of the forces and their distances, for the clockwise moment, it is C times the unknown distance, which we will call X in this case, because that's our unknown. No, we wouldn't call that X. Here's the thing. The distance here is measured, well, you'd have to call it X. Yeah, because at the very end, we'd have to find out what it is. But from the pivot to C, we'd have to find what that distance is, because the total distance is its moment distance. But at the end, we'd have to find what that gap is. But we know what the rest of it is, right? But we still call it X. All right, we still call that X because it's a part of an unknown. A part of it is
Excuse me.
yes.
Would it be to start from like C to A? Would it be 0.5 plus?
Right, but what I'm saying is the moment arm, the moment distance of C would actually be, well, we call this an unknown, but what we're going to say is that with regards to the distance of C from the pivot, we'll call that X. But a part of X we know. We know a part of X, you know, right? Because X now is the 0.5 plus our unknown gap of P to C. Understood?
Yes, sir.
Right. So we just want to find what X is, and then we can find what that gap they're asking about, because we already know the rest of it from the pivot point. All right, so we know that. The next thing we want to determine now are the distances of P to pivot and Q to pivot. So we say that P now will be multiplied by what distance? What's the distance of P to pivot?
0.5.
0.5 meters. Good. And then because it's a summation, we put this in brackets. And we put the force with the distance. And then we add. We have to multiply first before we add. And then we say Q, and what's the distance of Q from pivot?
1.5.
1.5. So by looking at the diagram, sketching the diagram, looking at it, we can now interpret our data correctly, and hence now it's just math from here on out. All right, so we know that C, we're gonna leave C for the time being as C, because we know what C is. The force at C is W, which is of course 1,000. All right, instead of writing out 1,000, but we're gonna write out now the values of P. We found P, we stated P, they gave us P as 600 in the first part of the question. And that's gonna be multiplied by 0.5. What happened there? Okay, right. And once we do the math from this point on, and that's added to Q, which is 400 times the 1.5. And remember, these are bracketed, so we have to work out the bracket first before we actually get the answer. So this is C now times X. All right, so 600 times 0.5, that gives us 300 Newton meter. Half of 600 there is 300. And then we multiply 400 by 0.5, that'd be 600. Newton meters. And then C times X is equal to 900 Newton meter. And then finally now we introduce what C is. So X now is equal to what C is, 900 Newton meter divided by what's the C value at the force at C is. So that's 900 Newton meters divided by the 1,000. I didn't get that. Say again.
Yes, sir, 1,000.
Okay. Newton. So Newton cancels Newton, and that gives us 0.9 meters.
0.4.
Right. And then of course, the value of P to C now would have be 0.4. Because we take the 0.5 from the 0.9 and we get 0.4. We all together?
Yes, sir.
All right, good. So that's how we'd work that part out for 5 marks. While I work it out, I know it looks simple, but that's the approach that you would have to take. When you deal with principal and moments questions, we just have to just take our time to work it out. All right. State why the center of gravity is located closer to point P than to point Q. Why is it that it is located closer to point P than Q? Let's see. The bay is horizontal, the weight must provide a clockwise moment to balance the anti-clock. Not so much, Trey. Remember, more mass, meaning that there's more mass on that side, on the P side. And also what you could say is that if you look back at am I sharing the screen here? I should be, yeah. When you look back at the data, the bar is 1,000. If this bar was uniform and the weight was exactly in the center, then P and Q would be equal. They'd be sharing the weight equally, but they're not. P has more weight than Q. Together they have 1,000, but P has 600, whereas Q has 400. So that means that the side of P has more weight on it of the 1,000. So that is why now, when it comes on to the center of gravity is located closer to point P than Q, because of the 1,000, P has more. So therefore, there's more mass on that side or more weight on that side. Understood? As Amarius had said, more mass on that side. To say more mass, Amaria, is incomplete. You have to say that there's more mass on that side because there's more weight on that side, and you can show that P now carries 600 versus Q. Are we all together on this?
Yes, sir.
Okay, excellent. All right, so we can now proceed to number 3, waves. What is meant by a transverse wave? In the charts or open your mic, speak to me. For 3 marks, what is meant by a transverse wave?
Sir, is it a wave that is produced from a perpendicular motion?
What do you mean by perpendicular motion?
Like,
Imagine now, I am not the physics teacher, explaining this to somebody. What do you mean by perpendicular motion?
meaning that the motion, the source of motion is moving into a left and right, is moving from left to right, creating the transverse wave.
All right, the first thing we should understand about waves is that they are disturbances that carry energy. So a wave is a disturbance that carries energy. Good? Now the disturbance creates an oscillation. From simple pendulum, you would have learned about oscillations. That when you have the ball and the string swinging back and forth, right? Oscillation. So when there is wave motion, there is disturbances that oscillate. And the oscillations can be in one direction or the other in terms of how the wave travels. Now, when I speak to you, wave energy travels from my vocal cords to the laptop, and then from the laptop speakers where you are, your device speakers, to your ears. So wave energy is always traveling from the source. Now, from the source, the direction of wave travel, the type of wave, whether it be transverse or longitudinal, will be determined by how the movement of the particles are. All right, that is what I wanted for you to tell me. So when the particles oscillate, they can either oscillate in a direction that is parallel to how the wave is traveling. So if it's traveling away from you, parallel means that the particles vibrate back and forth, away towards, parallel as the wave travels from you. The other direction, which is the transverse, is, as you were trying to say, perpendicular, is a direction that is up and down or left to right. But pretty much that direction, left to right, up and down, must be perpendicular 90 degrees to the direction that the wave is traveling. So to define the transverse wave, it is that wave energy where the particles oscillate or vibrate 90 degrees or perpendicular to the wave energy travel. I don't know if you all got that bit. Did you get that?
Can you repeat, please?
I'm saying when we look at wave energy, let me just quickly bring it up. Let's bring it up quickly. Waves. There we are. Let me show you real quickly what I mean by this. Longitudinal versus transverse. Stop sharing that. Let's see now. 1, 2, 3, 4. Let us. Right. The longitudinal versus transverse. So once this is a slinky coiled piece of metal. So the wave energy transport is left to right. However, for you to create longitudinal waves, you're moving your hand back and forth. So the wave energy, the disturbances travel parallel back and forth. So when you look at the red line, it's parallel to the energy direction. So this is longitudinal waves being created. Transverse move up and down, right? Or left to right, which is 90 degrees to the wave energy travel. Understood? We're good?
Yes, sir.
Okay. All right. So that is what this is saying here. And then you can look at sound waves there, and then look at the water waves there, transverse wave and that type of thing. All right. All right. So let's get back to the question we were looking at. All right. Give one example of a transverse wave. I just mentioned it.
So a slinky in a slinky.
Transverse wave light. Another one. Thank you, dear Marissa.
Water.
Water waves. Any other?
Electromagnetic.
Electromagnetic wave, which is light waves. You can also
AC
talk
current.
about. Say again.
AC current.
AC current. Here's the thing. AC current does have what they call a sinusoidal pattern, but the particles themselves do not emit waves like that. The current is as a result of oscillating charges, electrons within the conductor, but they don't radiate wave energy like that. Microwaves, yes. So all EM waves, three. Waves in a slinky, to be specific, yes, Akeem. Right? Waves in a string, waves on a spring, waves in a slinky. But when it comes down to AC current, they do have the similar pattern as transverse waves, but they're not waves in and of themselves. They just have the same oscillatory movement, which is back and forth within the conductor, but they don't emit wave energy like that. All right? All right, so we're clear on that. Define the term ultrasound. And the follow-up question to that is an application of ultrasound. Anybody knows what is ultrasound?
There are some waves with frequencies higher or with an upper audible
Upper
than the
audible
human
range.
hearing.
All right, let me just clear that up to you. You are on the right path, dear. Let me just clear it up for persons who are probably not following as to what that means. All right, let's try that again. I'm just trying to bring up the information that you should be aware of from current slide. Good. Let's bring it up. Let's try that again. Oh, here we are. Good. All right. So when I talk about the range of audible sound, we cannot hear all frequencies. There is a range of frequencies that we can detect as human beings. The older you get, the narrower this range gets. And different species of animals have different ranges. All right. And there's an upper and lower limit. So our range of human hearing is 20 hertz of vibration to 20,000 hertz. And you can see the different animals there. Right? Bats have the widest range because they use echolocation to navigate. So they have a very wide range. Dolphins also have a very wide range, but they're not listed here. Dogs have a range, upper limit range that is higher than us. So when you hear about dog whistles, dogs can hear them or we can't. The reason is that the whistle emits frequency above our range of hearing. So they can hear up to 45,000, we just stop off at 20. So the whistle does emit a sound, but guess what? We can't pick it up because our range of hearing now stops at 20,000. All right. So our range of hearing, just remember, 20 hertz to 20,000 hertz or 20 kilohertz. Now, as it relates to ultrasound, where is it? Where is it? Where is it? Does it mention it here? Yes, here it is. In medical diagnostic procedures, ultrasound, sound that has frequencies greater than 20,000 hertz. So any sound we're taking as reference because we're the higher order beings. So any sound that we cannot hear is considered to be ultrasound. So it's not the procedure itself, in and of itself, that is called ultrasound. The procedure uses ultrasound, and I'm talking about when pregnant women go to look on the fetus and the development and whatnot. The procedure uses ultrasound to give you an imaging of what's happening inside the uterus. But the actual thing that is used is sound waves that are emitted that we cannot detect using our ears. And once you exceed the upper limit, then it's considered ultrasound. So the question there, what is ultrasound? Sound waves or sound that has a higher frequency than 20,000 hertz. And an application of it is used in examining internal body organs or looking at the fetus of pregnant women and all of that. Dolphins communicate by emitting and receiving ultrasound vibration, as you said. They use that for communication, right? So yes, the dolphins also communicate using ultrasound, right? And bats do this as well. When you see them flying around and you believe that they're said to be clinically blind because their eyes that they have are not sensitive to light, but you can't see as good as them in the dark, right? And by seeing, they don't really see the way that we would see using our eyes. They use emitted sound frequencies that reflect and come back to them, and they just create this 3D image of wherever they are. All right, so those are the answers to that. So defining the term, anything above 20,000 hertz, example of application, medical imagery, or for fetal, checking on the fetus development. All right, so we're on to refraction. Figure 3 shows the path of a light ray from air through a cube of ice along the two rays showing partial reflection. So partial reflection is shown here, and well, there's a reflection taking place there. And the angles are given. Mn is the boundary of air to ice, and then the ice was within this boundary, Mno. All right, and we have a light of ray passing through the cube of ice. Now it says, determine the angle of incidence. Bring this out a bit. No, probably I should bring it back in. Right, it says, determine the angle of incidence on the face Mn. So, can we find the angle of incidence using the diagram here? Anyone?
Yes, sir.
What is it, Jonathan?
So the normal is perpendicular to the
The boundary.
baseline, yeah. So and you get the angle which is 31 degrees right there. So you just subtract the 31 degrees from the 90 degrees.
Right. So that's the key thing there. We should acknowledge that all angles must be measured from the normal. So even though they give 31 degrees, some person may jump and say, oh yeah, refraction incident angle is 31. No, that is a trap, and avoid the traps. So the angles must be measured from the normal. And since the normal is 90 degrees to the boundary, we know that this line, dotted line, is 90 degrees and as such to Mn. So if from Mn to the ray is 31, then from the ray to the normal must be 90 minus 31, which would give us what? 59?
Yes, sir.
59 degrees. So the angle of incidence is 59 degrees. Hold on to that number. What is the angle of reflection on the face Mn? We have partial reflection at
59.
Mn. Say again?
Sir, would it be 59? Because angle of incidence equal angle of reflection.
Good. So we have applied the concepts. We have applied the principles.
So where you get 59 again?
All right. Here's the thing. Once you're dealing with reflected rays, there are two laws that govern reflection. One law says the angle of incidence equals the angle of reflection. So from that, I don't know, I think it was Akeem, had pointed out that the 59 of angle of incidence must be equal to the angle of reflection, that partial reflection here, which would also be 59. Are we clear on that?
Yes, sir.
All right, good. Anshi, you want to say something? No? All right. So we're at now the angle of refraction at face Mn, given that the refractive index of ice is 1.31 for 4 marks. So how do you solve this one? Everybody get quiet. Why everybody quiet? Nobody wants to attempt
Sir,
this.
I never hear what you're saying, sir. About the
I'm saying
59.
we're now at the point where we want to find the angle of refraction.
No, sir. Go back to
Oh, you
incident.
mean the reflection thing?
The incident one.
Right. What I'm saying is there's a rule of reflection. All right. The ray that approaches the face MN, it is refracted, it gets inside the ice, which is this solid arrow, and then it is partially reflected, which is this dotted line going off. So they asked the question, what is the angle of reflection on face MN? So this is the arrow that you're asking about. And from the law of reflection, laws, two of them, but the more important one, it says that the angle of incidence of 59 degrees, which you just found, is equal to the angle of reflection. So any reflected ray, its angle from the normal and the angle of incidence will be equal. Understood?
No, sir. When they ask, so you get the angle of incidence, not the refraction.
All right. The angle of incidence at face MN. The normal, this dotted line is 90 degrees to MN. And then the actual angle of incidence must be between the ray and the normal, not the ray and the boundary. So they have given you the angle of 31 for the ray to the boundary. And you may be tempted to take that as the angle of incidence. It is not. That is just the remainder of the angle that would be the angle of incidence, because you'd have to measure it from the normal. So from the normal to the ray must be the 31 minus the 90, because the normal and the boundary are 90. So when we take 31 from 90, we get 59 degrees. Understood? Yes?
Yes, sir. Yes, sir.
Okay, good. All right. So 59 is this one. 59 is also that. We're now at the angle of refraction on face MN, and we're given that the refractive index of the ice is 1.31. So how do we solve that?
You will use Snell's law equation.
All right,
N is
Carissa,
equal
what is
to-
Snell's law equation?
N is equal to the sine of the angle of incidence over the sine of the angle of reflection.
All right, good. So let's go now to the whiteboard for that. Where am I? Where am I? Where am I? Where am I? I've lost my whiteboard. All right, try that again. No, not that. All right, close this. Here we are. Good. All right, so Carissa has said that Snell's law tells us the sine of the angle of incidence and the sine of the angle of refraction. When you divide those two, we get the refractive index. All right, so we know that the refractive index of the ice is 1.31. We also know that the angle of incidence is 59 degrees. And we want to find the angle of refraction. So that's an unknown. And based on what Carissa has suggested, she has suggested that the refractive index is equal to the sine of the angle of incidence over the sine of the angle of refraction. But here's the thing now. All right, we're going to work it out. And then I'm gonna just give a little extra there. So we're gonna take the n value as being 1.31. And then we take sine of 59 degrees over sine of theta r. So we're putting now the value that we know, and we can identify what we need to find. So transposing now for sine R, first of all, we have to keep sine attached to theta R until the very last. So throw it away. So when we transpose now, what do we get on the right hand side?
1.31 times sine 59.
No.
Sine 59 over 1.31.
That's it. Sine theta R would go up and multiply by 1.31. When we bring 1.31 over, it divides. So I believe it was the name Benz there. Yeah, you have to be careful of the transpositions. You have to be careful. All right, because when you multiply, you're gonna get a completely wrong answer. All right, so when we sine 59 sine function, we get 0.857. Five, 7 over 1.31. And then that now would be, and then we divide that now by 1.31, and that gives 0.654. All right, so at this point now, what do we do to find theta R?
Sine inverse.
Sine inverse, good. So we sine inverse that answer of 0.654.
40.86 degrees.
And then we get, we get 45 degrees. Is that the answer?
About 40.
Sir, 40.
86.
40.86, 40.9, you can even say 41. You want it to have to be approximately 41 degrees. All right, now, I don't know if you are given this equation that I'm going to bring to your attention, but I'm going to bring it to your attention. And the reason why I'm going to do that is because I don't want it to be a case that you run into a question that requires you to solve it another way and you're not able to. So let me just, maybe I should have zoomed this in from the very get-go, and then, all right, so that's the workout that you did there. I don't know if anyone has seen this type of equation where it's a N1 sine theta I is equal to N2 sine theta R. Has anyone ever seen this equation?
No, sir.
No, sir.
All right, here's the thing. This equation is the general diffraction equation. The equation that you would have been given is, it can apply, and it has applied, but the challenge with this equation above is that you must always have the ray of light coming from here to the material. Now, if you have it coming from the material to here, you couldn't use this and get away with it. You'd have to modify it. If you had it coming from glass to ice, or glass to water, whatever the case may be, you'd run it, you couldn't use this equation above. Right? Now, the general equation here can be modified to give you what you want. Now, one would be the material it's coming from, and N1 would be the refractive index of the material it's coming from, which in this case is air, and N2 will be the refractive index of the material it's going to. All right? And of course, you know, sine theta I and R. So here's the thing. If we cross multiply. Say we bring over n1 to the right hand side and sine theta r, this should be r here, to the left hand side. So if we bring over this and that, we'd get now sine theta I over sine theta r, which you're familiar with, right? And then on the other side, we would have n2 is the right side,
over N1.
right? Now here's why you got away with this up top. So when you look at the two equations, this here, let me highlight it, this, and what we're going to be looking at. So we're looking at that one. The reason why you got away with this one is because n1 here is actually 1. So it'd be 1.3 for the ice over 1. So that checks out. So that's why you get 1.3 here over that. Now imagine if you're coming from ice to air. N1 would be the ice, which would be in the denominator, and then 2 would be the air, which would be 1. You understand? It would still be sine I over sine r, you know? Because sine I is where it's coming from, sine r is where it's going to. So that doesn't change. This is Snell's law. But the N1 and N2 now, it all depends on where you're coming from to where you're going to. So from here to the material, you get away with it. Because N2 is the material, N1 is air, and once you divide anything by 1, you're good. But if you're going in the reverse direction, it's not going to be correct. Are you see what I'm saying, students?
Yes, sir.
Right. So the safer equation is this one. N1 sine theta I is equal to N2 sine theta r. This deals with any two materials, any direction. If you use this up top, you're going to have to have a situation where it's going from here, always from here to the material. If it's going the opposite way, or if it's going between two different materials, then you can't use this. So this is a limited equation. All right, so I'm giving you the general refraction equation. Write it down. General refraction equation in which this now deals with any two materials with the rays going any way. And once you know how to identify the terms, then you can solve your question. All right, so that's why I said I was going to work with what Carissa had said first, and then I'm going to give you now the general equation. Because CSEC may not necessarily send you a question that deals with air to a material. They may just ask you now from two different materials or from a material to air. They assume that you would know this. So I'm giving it to you. Ensure you add this. Don't throw this away. This is still valid to an extent, but this is a general equation. All right, so please try to use this more than that one up there. If it's air to the material, fine, you can use this, get away. If it is not, then you have to use this one. Are we clear?
Yes, sir.
Yes, sir.
All right, lovely.
Yes, sir.
All right, let's see now, where are we? I believe we're here. All right. You found the refractive 41, the angle of refraction 41. On the diagram, label the critical angle for ice. So where would this critical angle be? And by the way, what is critical angle? Somebody talk to me. What is critical angle and where is it? Nobody knows? Nobody? Somebody? Nobody? All right. The
I
critical
think
angle. Again?
it's where the angle of refraction is 90 degrees.
All right. Yes. Technically speaking, the critical angle. All right. When I'm showing the critical angle, I always go to a video that deals with it. It shows, it's a short video. It goes straight to what it's all about. I always try to just use that, that diagram. Starting an online store is easier. Let's get rid of this. All right, so let's see now. Stop share. Go to share sound, optimize a video clip. Yeah, this is it. Right. So what I'm going to show you now is what critical angle and total internal reflection is all about. All right, so what the person here has now is a perspex block. I think it's either perspex or glass, prism of the sort. So they're shining light there, right? So everything is along the normal, so that's good. No deflection there. All right, now at 10 degrees incident, so the incident angle here is 10 degrees. The refracted angle is about 13 degrees up top there. Good, so refraction is taking place there. All right, at about 30 degrees, it's about 45 degrees refracted angle. At about 35, it's about 56 degrees. As we progress, as we progress, as we progress. So the more and more the angle of incidence come in. Now notice, at near about 40, you can see a reflection coming in, right? This is what we call total internal reflection. The ray is bent so strongly that it is reflected within the material. It's not like this material becomes a reflector. It is bent so strongly that it becomes reflected within the material. So at 40 degrees incidence, we're at about 73, 74 degrees of refraction. Now, right about there, at about 42 degrees, the ray has completely disappeared in terms of refraction. At that point, what has happened is that the ray is now refracted along the boundary. So once we have a refracted ray that travels along the boundary, we call this angle of incidence the critical angle. The ray is about to be internally reflected. As a matter of fact, it is already there. So when we talk about critical angle, we're talking about that angle of reincidence that causes the ray to travel 90 degrees of refraction or along the boundary. Anything beyond the critical angle, we have, so the person is going to pause it there, right about there. So that is the incidence, critical angle of incidence. Anything beyond that point, the ray now becomes internally reflected. As you see, when you start increasing it now, the laws of reflection come in. So we see as the incident angle increases, the reflected angle increases. Are we all clear on this?
Yes, sir.
Yes, sir.
Yes? None of the persons are still there. Are you still there, students?
Yes, sir.
Yes, sir.
Are you still there?
Yes, sir.
Yes.
Okay. All right. So I just wanted for you to be clear on that. Now, as it relates to the question to label the critical angle, where would this critical angle be on the diagram? Do we know? All right, what I will do, let me see if I can I wonder if I could write. No. See if I can write on it. I don't think I can. All right, where this is right here. This angle that's right here. Between this ray and the normal there, that is your critical angle. All right, that is where your critical angle would be. Between this ray and the normal that is there. All right, and the reflected ray will go this way. All right, so I've done that part. All right, let's see now. What I'm gonna do is that I'm gonna focus on the motor question in case I will run out of time. So let's focus on this motor question. What question did you look at? Number 3 was that? All right, so let's focus on this motor question. It says here, figure 6 shows a simple DC motor which consists of a coil of wire ABCD between the poles of a magnet. The dotted line represents an axis about which the coil can turn. A current flows through the coil in the direction showed by the arrows. So the current comes in from D, goes up to A, across to B, down to C, and out. It says, draw the magnetic field between the poles of the magnet on figure 6. So how the magnetic fields point based on this?
We could draw perpendicular.
Hello? Persons are there?
Draw the lines horizontally from
Why do you get
the
quiet
south
from
pole
Mr.
to the
Auburn?
north pole. You hearing me, sir?
Anybody here? Yeah.
Yes, sir.
I don't know. They are talking, but I'm not hearing them. All right, hold on. Let me stop sharing that. Don't know what happened there. All right.
So you draw horizontal lines from the
Could
south
somebody
pole to the
speak?
north
So
pole.
just let me confirm I can hear somebody. As I'm not hearing. Anybody?
Yes, sir. I hear you now.
All right, see persons trying to talk, but you can hear, but apparently you can't hear us. I'm wondering why that is. Hold on. Let me close this. Ever since I opened up that YouTube thing, it's been misbehaving. You would draw the horizontal lines from the north to the south, from south to north pole. All right, horizontal lines, yes, Devon, but from south to north, meaning pointing from south to north, no. Magnetic field lines point from north to south. All right, north to south. So they will point horizontally from the right to the left. That's how they would point, from right to left. But yes, there would be horizontal lines extending from across, from north to south, and a point north to south. Say the direction in which the side dA of the coil will move as the current starts flowing to the current. So this is where now Fleming's left-hand rule comes in. Do we know about Fleming's left-hand rule?
Sir, isn't it right on?
Yes, sir.
Yes, sir, I know about the left hand rule.
Do we know about Fleming's left-hand rule? All right, the right hand is for the generator band. All right, generator is right-hand rule. The motor is a left-hand rule. All right, and the left-hand rule, if you're looking at the video, force on the conductor, field from the magnet, current flow conventionally. Force, field, current. And this is how you set your fingers. All right, now, in terms of finding where the direction, what is it? The direction on which the coil will move or if you want motion, force or motion, all right, force which causes motion. Now to find how it is, you'd first need to set up your finger, or rather, well, it's north to south, so it will be pointing across, right to left. And then the current on this side, which side is it? DA, right? D to A, which is on that left side, is going in or up on the paper. So it's up on the paper, the field is across, right to left, up, right to left. Your thumb is pointing towards you. So that means that that side of the coil is actually going to move up out of the page. All right, it's going to move up out of the page and want to go over to the right-hand side. So the current is up, the field is across, the force is going to be up out of the page. All right, name the rule used to determine the direction in which DA moves. That is the Fleming's left-hand rule, not right-hand. The right hand is generator. This is motor. Generator and motor are opposites of each other. Whatever you use to power motor, you use the opposite now to generate electricity from a generator using motion. So it is up out of the page. The answer to that one is the generator rule. Explain why a split ring commutator is using a DC motor. And that's for 2 marks. Does anyone know why there's the use of the split ring commutator? Do we know what a split ring commutator
Is it
is?
used to like ensure that the coil continues to rotate in the same direction?
Anybody?
Seems as if he's not hearing us. You're going to have to
No
type it.
responses there. All right, as it relates to the split ring, when you're dealing with the DC motor, the current from the DC motor, the supply current, does not change direction. However, because the coil, see your response here. Right. I don't know. I'm not hearing the audio at all. I don't know what is happening. All right, let me see if I can figure this bit out, because persons are speaking, but I'm not getting any audio across at all. I don't know what happened. Let's see now, turn out that. Oh. Computer audio. All right, how about now? You hear me? Respond, anyone?
Yes, yes,
No?
sir.
Sir? Sir, we can just
I
continue,
really
sir.
don't know what's happening. Yo, I heard you earlier on, and now I'm not hearing you at all. Share sound. I don't know what's happening. I really don't know. I didn't resume share, pause share. I don't know what happened, but yes, to keep the motor going in the same direction, even though the coil is turning over, right, is what, all right, I know you can hear me, all right? So I guess that's the important thing right now, because you can respond via text if necessary. But yes, the motor here needs to keep on turning, even though it's going over on the other side where the force now will change direction. So you don't want when it flips over, the current is not able to change direction as well. So the split ring allows for the current to change direction in the coil, not on the outside, but in the coil. Right? Because once you have the split ring, it can break contact and make contact. So you can allow for current to change direction in the coil. All right, figure 7 shows a graph of variation of voltage with time across the output terminals of an AC generator. All right, we have voltage in volts, or we have a sinusoidal curve, up, down, it varies continuously. And we have time now in seconds, voltage in volts. Calculate the value of the frequency for this generator. So, how do we find the frequency for 3 marks? Looking at that. All right, speak now. I believe I muted my audio. Will you speak now? Somebody speak.
Use the equation F equals 1 over T.
I turned on my audio. Yes, say again, Carissa.
Use the equation F equals 1 over T.
Right, good. F is equal to 1 over T. And what is T?
Is 0.02.
0.02. So the period of the wave is 0.02, right? And then we do F frequency is 1 over T. So that would be 1 over 0.02, which is the same thing as 1 over 2 over 100, which is inverse, gives you 100 over 2, which is 50 hertz. Yes. All right, so once we divide 1 by 0.02, we get 50 hertz. All right, so that's the answer there, 50 per second or 50 hertz. The peak voltage is applied across the generator. Peak voltage applied by the generator across a 100 ohm resistor. Calculate the peak value of the current in the resistor. If we're given voltage and we're given resistor, how do we find current? What law do we apply? All right, Carissa, I see it. F is equal to 1 over T. Yeah, speak to me now. The audio came back. I turned off my audio on the thing there and then turn it back on. Ohm's law, good, okay. All right, what does Ohm's law state? What's the equation for Ohm's law? V is equal to IR, good. And then if we solve for I, what's the equation for I? V over R, excellent. So the V value, the peak value of V would be what?
200 volts.
200 volts, good. And then the resistor value was 100. So that's pretty much 2 amperes of current that we would get there for the answer. The generator is subsequently rotated at twice the frequency. Say the effect this will have on the period and the value of the output voltage. So at twice the frequency, what happens to the period? Will the period stay the same? Will it increase or decrease? Thank you there, Trey, for the 200 volts.
Increase.
The period would increase. All right.
Decrease.
It would decrease. Remember, the relationship between frequency and period is an inverse. F is equal to 1 over T, therefore T is equal to 1 over F. So if the frequency increases, period, which is 1 over F, if F becomes larger, the fraction overall becomes smaller. So once the frequency goes up, the period has to become smaller because the frequency tells how many wave cycles per second. So if the wave cycles per second increase, that means the time for one cycle must go shorter or lesser. So the frequency increase results in a period decrease. All right, frequency goes up, period goes down at the output. The value of the output voltage, what happens to that? What happens to the value of the output? Do it stay the same, increase or decrease?
Would increase.
Say again, Carissa, I didn't get that.
It would increase.
It would increase because once we are spinning the generator faster, then we're making the interaction between coil and magnets more rapid. And once that becomes more rapid, then the output voltage would go up. All right. So spinning the generator at twice the frequency makes the period smaller, half as much, and the value of the output voltage will double. All right. All right. Permit me now. I know that we're about a few minutes, but just permit me to just go through this last one, and then we can call it an end. Radium-226 is radioactive and represented by the nuclei 226 over 88 radii. Radium. For the neutral atom of radium-226, state the number of protons. How many protons are in radium based on the nuclide statement there?
88.
88, good. Number of neutrons. That is it, Trey, 88, yeah. Number of neutrons.
138.
138.
88.
Subtract, right, 138 is found by subtracting 88 from 226. Mass number minus proton number gives number of neutrons. Number of electrons for the neutral atom.
88 as well.
88 as well. Once it is neutral, number of protons and electrons are equal. Good, good. A radium-226 nucleus decays by alpha emission to radon nucleus. What is meant by the term radioactivity?
So is the emission of radio waves from an unstable atom.
Right, unstable nucleus. And what is the end result of this emission?
Unstable atoms.
Why does it emit the radiation?
To be more
Because it's
stable.
unstable, but what is the end result of it?
So to become stable.
To become stable. So it is the emission of radioactive material, or rather emission of particles or energy from an unstable nucleus so as to become more stable. All right, so you have to state that it is from something that is unstable, something is emitted, and it needs to get more stable. Complete the equation for the decay of radium-226. So what would you get at the end?
222.
222 at the top.
And 86.
86 at the bottom with R. Right,
Plus,
and then what would you
the
get
alpha
now as plus the alpha particle, which is 4 at the top, 2 at the bottom,
And 2 at
and what is it
bottom.
represented by?
Plus energy.
Plus energy. And what is the alpha particle represented as?
A helium nucleus.
Helium nucleus. Good. Radium-226 has a half-life of 1,600 years. What is the term half-life? What does that mean?
The time taken for half the amount of a sample to basically
Decay.
Decay, yeah, to decay.
Right. So it is a time taken for half the remaining sample to decay. All right, time taken for half of the remaining sample to decay. All right, at a certain time, a sample contains that radium nuclei. Calculate the number of alpha particles emitted by radium in the next 4,800 years, and then how much more time elapses. All right, so at a certain time, a sample contains that. Calculate the number of alpha particles emitted by the radium nuclei in the next 4,800 years. Now, how do we find the number of alpha particles emitted by the radium nucleus? Not so sure. All right, what we'd have to do is to find the number of particles at the start, which we know, and the number of particles at the end, and then we'd subtract them. Because that now, for each radium nucleus that decays, an alpha particle is given off to give radon. So we have to acknowledge that. Each radium nucleus will emit an alpha particle, because it says a radium nucleus decays by alpha emission to that. So each of them emits an alpha particle. So our job is to find how many particles are at the start, how many particles are at the end, and then we subtract those two numbers. All right, so how do you find that? All right, we can work.
By finding the number of half-lives.
We can find the number of half-lives. Good. So how many half-lives will have expired in 4,800 years? 3. All right, how did you get 3?
The equation t to a half is equal to total time. And then you would
E to a half is equal to what?
total time over n, which is the number of half-lives. N is the number of half.
Total time over n, which is the number of half-lives being n. All right. So the total time is 48. N is the number of half-lives. And the half-life there is 1600. So when we transpose for n, we'd simply have 4800 over 1600, which gives us the 3. So we divide the total time by the half-life to show the number of half-lives. So 4800 divided by 1600 gives 3 half-lives that would have expired, right? And then what do we do now with that 3? We know it's 3 half-lives that would have expired. So we'd have to find out how much reduction would have taken place. Yes? So for 1 half-life, we would divide the initial particle amount by 2. But it's not 1 half-life, it is 3 half-lives. So what would be the reduction factor after 3 half-lives? If 1 half-life is 2, then 2 half-lives is how many?
4.
4, and then 3 half-lives is how many?
6.
No. No.
8.
8. With half-lives, we raise the factor of the number 2 by the number of half-lives. Because remember, it is the time taken for the initial amount to reduce by half. So if you have 1, after 1 half-life, 1 becomes a half. Then you have a half. That half is further reduced to half its original, which is a quarter. And then that quarter is reduced further by a half, which is an eighth. Not 6, but an eighth. So it essentially divide the initial amount by 8. When we divide this initial amount by 8, what do we get?
16.
No, we're dividing it by 8. We're dividing the sample amount, the initial sample amount by 8. What do we get?
200.
What is the initial sample amount? It says at a certain 8 times 10 to the 8. So that's the initial sample amount. If we divide 8 by 10 to the 8 by 8, what do we get?
10 to the 8.
Say again?
1 times 10 to the 8.
1 times 10 to the 8. So the sample of 8 times 10 to the 8 after 3 half-lives, after 4,800 years, would have fallen to 1.0 times 10 to the 8. So what is the decrease then? How much of it has been lost?
7.
7 times 10 to the 8. And that is the number of alpha particles that have been emitted. Understood? Are we clear?
Yes.
Right. So we have to first work out the number of half-lives. Then we work out what it has been reduced by using the number of half-lives, 2 raised to n. And 3 being n, then 2 raised to the 3 gives 8. So we reduce that by 8. 8 divided by 8 gives 1. So at the end, it is just 1 times 10 to the 8. So the reduction amount is 8 minus 1, or rather 1 minus 8, which is negative 7 times 10 to the 8. So that is the number of alpha particles that have been emitted. And finally, how much more time will elapse before the number of radionuclei remaining fall to that? So we're now at 1 times 10 to the 8. How much more time do we need now for it to fall to 0.5 times 10 to the 8?
We need one.
We need what?
1 more half-life.
Which is how much?
With 6. 1600 years.
Right, so we need 1600 more years for it to fall to 0.5 times 10 to the 8th. Are we clear?
Yes, sir.
All right. Now, with regards to the wave question, where was it? No, not waves. The temperature question, gas law question, which is this? Because we looked at, yeah, we looked at that. I don't know how much time you would have left, because I know that some persons are going to be in the chemistry section that comes up, and that starts in the next 2 hours. But is it possible for me to just run through this real quick, or no?
Yes, sir. Run through.
All right, run through, cool. All right, so 4A, on figure 4 below, sketch a graph of pressure versus temperature in degrees Celsius for an ideal gas. In terms of pressure versus temperature in Celsius, first of all, it's a straight line graph with a positive gradient. But if it is in degrees Celsius for the ideal gas, it will not start at 0, 0. It will instead start at what we call it now. Let me show you what I mean. Because when you're dealing with degrees Celsius versus Kelvin, we have to know what each graph, is it right? What each graph represents. All right, so when you're dealing with, let's draw these graphs real quick. That's one, and then the other is here. Right, it's behind the x-axis. Right, to get the Kelvin scale. All right, so we're gonna extend this a bit. Should I move this up? I drew this wrong. All right, let me extend here. Good. All right, that is there, and this is here. Good. All right, so in terms of the Kelvin scale, it would be pretty much like that. And for the degrees Celsius scale, it would be like this with the line extending backwards like that. Right, like that. So this would be pressure. No. Right. Yes, this would be pressure versus, and of course, this would be pressure in pascals if you want those units. And this would be temperature in Kelvin. So at 0 Kelvin, you have 0 pressure. But for this one now, with pressure in pascals versus temperature in degrees Celsius, at 0 degrees Celsius, you still have some level of pressure. So this now is marked as negative 273, which corresponds to 0 Kelvin. All right, this is 0 Kelvin. So when they ask you for the distinction between the two, you have to state, you have to acknowledge the fact that with 0 Kelvin, it is a graph that extends like that. All right, you have to acknowledge that. Cool. If it's Kelvin, it's 0, 0. With degrees Celsius, it starts, there's going to be a y-intercept, and then it can be traced back to the 0 Kelvin there. All right, negative 273. All right, so we're clear there. Then where are we now? I'll explain how the graph could be used to derive the Kelvin scale. In terms of the graph, as I said, you'd have to trace it back. So you would show the sketch, and the sketch would stop somewhere up here. In terms to derive the Kelvin scale, what you could do is that you could extrapolate. You extend the graph, extrapolate the graph to touch the x-axis, and wherever that point touches the x-axis now, you can now use that linear relationship, right? So to explain this, you would now extend the graph to touch the x-axis, and then you determine the relationship, or well, you could just find whatever the value is in degrees Celsius, and that would correspond to 0 Kelvin. And then from 0 Kelvin, you can now find a relationship between pressure and temperature. But the key thing is that you would have to extend the graph to touch the x-axis. And whatever value that in degrees Celsius, that would correspond to 0 Kelvin. And once you know 0 Kelvin, then you can find a relationship between pressure and temperature. But the key thing, the graph has to be extended. Using T to represent Kelvin temperature and degrees Celsius to represent, say, the mathematical relationship, yes, right, that's it. The temperature in degrees Celsius, temperature in Kelvin is the degrees Celsius plus 273. And the the degree Celsius is the Kelvin temperature minus 273. So if you have 0 degrees Celsius, that is 273 Kelvin. Right, and if you have 27 degrees Celsius, that's 300 Kelvin. So whatever the temperature in degrees Celsius, you add 273 to get Kelvin. And if you're given the Kelvin temperature, you must minus 273 to get the degrees Celsius. So 0 Kelvin is minus 273 degrees Celsius. Thank you there, Trey. In terms of the container stores 5 meters cube of gas at a pressure of 13 atmospheres and a temperature of that. Calculate the volume of the same gas that would occupy a temperature of that and atmospheric pressure of that for 5 marks. So the equation that you use here is the general gas equation, right? The general gas equation, which states pressure 1, volume 1 over temperature 1 is equal to pressure 2, volume 2 over temperature 2. Once you recall that equation, the volume 1 would be the 5 meters cube. The pressure 1 would be the 13 atmospheres, and the temperature 1, you'd have to convert this to Kelvin. Please, when they give you temperatures in degrees Celsius, please remember to convert to Kelvin if you're working gas law questions. If you do not, it's going to be wrong. Please remember to convert your temperatures to Kelvin if given in degrees Celsius, of which they would. All right, so the negative 273, the negative 23 rather, degrees Celsius, you add 273 to that, that will give you about 250 Kelvin, yeah? Right? So 250 Kelvin for the initial temp, and the final temp is 300 Kelvin. Did I get it right? I believe so. Yes, 300 Kelvin. So in terms of the initial volume, 5 meters cube, initial pressure, 13 atmospheres, initial temperature, 250 Kelvin. The volume final is unknown. The final temperature is 300 Kelvin, and the final pressure is 1 atmosphere. And once you transpose correctly, right, let me just ensure that we get the transposition correctly there. Once you'd have transposed correctly, then you would have gotten the solution there. So if you have pressure 1, volume 1 over temperature 1, or initial, whichever way you want to say it, is equal to pressure 2, volume 2 over temperature 2. All right, so if we transpose the first, to transpose correctly, we cross multiply. All right, for the safety of it all. So that gives us on one side pressure 1, volume 1, temperature 2, and that's equal to pressure 2, volume 2, temperature 1. And we're asked to find volume 2. So at the very end, volume 2 is equal to pressure 1, that's on the left side, volume 1, that's on the left side, temperature 2, also on the left, over pressure 2 times temperature 1. And when you insert those values in the correct units, then you would get your answer. All right, but that's how you transpose that. And then the other part is block X and Y are identical except for their temperatures. Explain the difference in the motion of the particles in block X compared to the motion of particles in block Y. The higher temperature means that the particles are moving faster, colliding more frequently, and generally they're going to have higher energies. Right? So they're faster motion, more collisions, more frequent collisions, and they're going to have higher energies. In which direction will thermal energy be transferred? Naturally, heat always flow from high temp to low. That is correct. Good. So it flows from X to Y, down. And finally, state the conditions under which the transfer of thermal energy would cease when both temperatures would become right. When they reach thermal equilibrium, when both temperatures are registered as being the same. Thank you, dear Trey and person that was responding. So I hope that what we've gone through will greatly assist you in your revisions, in your preparations. Just always remember that in any question that is asked, you have the content. It's clear that you have the content. It's just about interpreting the question correctly. As to what is coming, that's anyone's guess. All right, we can only hope that what you prepare for, what you focus on, is what they said. If they send something that you're not so familiar with, don't worry. There's paper 1, there's the S.D.A that will help you out. All right, so do your best. I know that you will do your best and you will do well. And I hope and pray that your performances will reflect on your grades that you will get. And quite frankly, I expect all passes from everyone, right? Of course, the grade 1 is there, distinction is out there to be gotten, but we have to prepare ourselves to get the grade that, will transpire. All right, so don't feel too down if you don't get the grade 1, but I am hoping and praying that you all work and do attain onto that grade 1. But I'm confident that you will all be able to pass. So I thank you for your time. I thank you for your interactions, and I hope that whatever was done since today was beneficial to you. Okay?
Yes, sir. Thank you very much.
All right, no problem. So you take care of yourselves and, all the best in your exams.
Thank you, sir.
No problem. Go.
All right, thank you, sir.
Cool.
All right, anybody hearing me? All right, we'll resume at 1 o'clock for chemistry. So you can go and get some lunch, and then we'll resume at 1.